Hey everybody, it's Miss Berry. We are starting chapter 4 today, which is called Probability, Randomness, and Uncertainty. And then specifically, we're going to go over section 4.1, which is an introduction to probability. All right, so let's get started. So the first thing we're going to talk about in relation to probability is how we identify the outcomes in a sample space or an event. So let me tell you what the definitions for sample space and event are. So a sample space is the set of all outcomes, so all the possible outcomes that could result for a given probability experiment. The experiment is just the whatever operation that you're carrying out under those controlled conditions. And an event is defined as the subset of all of the outcomes from the sample space. Right, so an event is typically denoted by a capital letter, so we might try to name that something meaningful, like if we are rolling a dice, we might say, okay, we're going to call the event E, the event of rolling an even number. Or we might call, let's say, A, if we're talking about maybe you're a telemarketer, the event A is going to be the event that someone answers the phone. Right, so you name events with capital letters, and we try to name them something meaningful. That way, when we look back at that later, it makes sense in context. So one notation that you're going to see me use over and over again in this chapter and in the future chapters, and I think in the next chapter 5 as well, is you're going to see me do this capital P and then a parentheses. All right, so when you see this notation, that means probability of. And then inside of those parentheses, we'll put whatever the event is. So maybe the probability of rolling an even number. All right, so probability of is that notation, the P with the parentheses. All right, so if you see the P with the parentheses, that means probability of. And then inside of the parentheses is the event that we're interested in finding out about. All right, so let's start out by just writing out a sample space for a given experiment. And since a sample space is the set of all possible outcomes, we are going to use what we call set notation. And set notation just uses these curly braces. All right, so since the sample space is the set of all possible outcomes for a given experiment, we are using set notation, which is the curly braces. And you have those on your keyboard. They're right beside the letter P on our keyboards. All right, so in this particular experiment, we are tossing 3 coins. All right, so we're supposed to use the letter capital H to indicate heads and the letter capital T to indicate tails. All right, and we're going to be super careful about using capital H's and capital T's. Since that's how we were asked to write those. All right, so if we're tossing 3 coins, each coin could have a heads or a tails. All right, so our first option is we could have, for each coin, we could have a heads or a tails. All right, so for the first coin, you could have a heads or a tails. And you can create what we call a tree diagram to help you identify all the possible outcomes, and that's what I'm about to do here. So let's suppose that you toss the first coin and you end up getting the heads. For the second coin, you have 2 more options. You could also get a heads or a tails. All right, so let's just follow this tree diagram. So let's say you get heads for the first coin and heads for the second coin. Once you toss that coin, that third coin, you could also get heads or tails. All right, and then again, if we follow the tree diagram, suppose we had heads for the first coin and then we got tails for the second coin. Once again, on our third toss, we could again get heads or tails. All right, and then the same thing is going to happen for the first in the event that our first coin ends up being a tails. So when we toss that first coin, if we get a tails, on our second toss, we could get heads or tails again. All right, and so let's just follow the tree diagram. Let's say we get tails on the first coin, heads on the second coin. Once again, we split off into two. We could get heads or tails for the third coin. All right, and then again, let's follow the tree diagram. If we got tails for the first coin and tails for the second coin, we could once again get heads or tails for the third coin. All right, so now we're going to write out all of these outcomes. So we could have heads, 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 tails, heads, tails, heads, heads, tails, tails. All right, so we're just going to write these all out. All right, so do your little set notation. All right, so we could get heads, 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 or we could get heads, heads, tails. All right, so that was just me following that first limb of the tree diagram. So we could get heads, 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 or heads, heads, tails. All right, now moving on to that second branch in our tree diagram. Heads, tails, heads, or heads, tails, tails. All right, so that's my next two. Heads, tails, heads, or heads, tails, tails. All right, moving over to my second tree over here, following this branch. Tails, heads, heads, tails, heads, tails. All right, so let's write those down. Tails, heads, heads, tails, heads, tails. All right, now following the second branch, tails, tails, heads, tails, tails, tails. All right, finishing this up. Tails, tails, heads, tails, tails, tails. Close your curly brace. All right, so a tree diagram is a great way to help you identify all of the outcomes in a particular sample space. All right, so let's count up how many options we had here. We had 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes in our sample space. All right, so depending on how many times you're tossing the coin, like imagine you were tossing the coin 30 times, this sample space could get really large. So it might not be realistic for you to draw a tree diagram every time. So I'm going to show you like a little shortcut way that you can identify how many outcomes are supposed to be in your sample space. Okay, so when you are trying to figure out how many outcomes are in a sample space, you can think of each little step in the experiment. I like to think of it as a little box. All right, so I'm going to show you how you can figure out the total number of outcomes in the sample space. So my first coin, I'm thinking of that as a box. My second coin, I'm thinking of that as a box. And then my third coin, I'm thinking of that as a box. So then I'm going to revisit that first coin and I'm going to think to myself, how many options, how many outcomes do I have for this first coin? I could either get a heads or a tails. So I only have two possible outcomes for that first coin. For the second coin, I have the same number of outcomes. When I flip that second coin, I could get a heads or a tails. So I have two possible outcomes for that second coin. And for the third coin, again, I could either get a heads or a tails. All right, so these are three identical coins. They both have a heads or a tails. All right, so now what I can do is I can multiply each of those numbers together to figure out the total number of outcomes in the sample space. So if you remember from the last slide, there were 8 possible outcomes in the sample space. So this is called the fundamental principle of counting. The fundamental principle of counting. And this is a super quick way to figure out how many outcomes are in your sample space. All right, so you can just think of each step in your experiment as a box, and then in that box you're going to put the total number of outcomes for that step in the experiment, and then you multiply those values together to find the total number of outcomes in the sample space. All right, so here is another little example where we are going to write out the sample space. It says, write out the sample space for the given experiment. Use O for olives, C for cucumbers, H for ham, P for pepperoni, R for ranch, and I for Italian. It says you are the server at a restaurant and your customers are deciding what they want to put into a salad. They can choose one extra topping, olives or cucumbers. They will add one meat, ham or pepperoni, and then lastly they must pick one dressing, ranch or Italian. All right, so before we begin, we can figure out how many outcomes are supposed to be in our sample space. All right, so I have three options. I have a topping, I have a meat, and a dressing. All right, so I'm thinking of each of those as a box. In the box, I'm going to write how many choices I have or how many outcomes are possible for toppings. I could have one of two toppings. I can either have olives or cucumbers, so I have two options there. I have two choices for meat, and then I have two choices for dressing. So I'm going to multiply those to find the total number of outcomes in the sample space. So 2 times 2 times 2 is 8. So I'm expecting to see 8 total outcomes in the sample space. All right, so I have a topping, a meat, and a dressing. All right, so for my topping, I can either choose olives or cucumbers. If I'm following the tree diagram, my next choice, if I choose olives, then I could also choose ham or pepperoni. And then from there, I can choose ranch or Italian. All right, so and then you can see I've got the same thing over here for if I chose cucumbers as my topping. All right, so just filling in the little tree diagram. All right, and so now I can write out my entire sample space. All right, so olives, ham, ranch, that's my first, following the first branch of my tree on the left, olives, ham, ranch. I could also have olives, ham, Italian, or olives, now I'm following this line, olives, pepperoni, ranch, olives, pepperoni, Italian. All right, so olives, pepperoni, ranch, olives, pepperoni, Italian. All right, now moving over to the cucumbers, cucumbers, ham, ranch, cucumbers, ham, Italian. All right, so cucumbers, ham, ranch, cucumbers, ham, Italian. All right, and then cucumbers, pepperoni, ranch, cucumbers, pepperoni, Italian. All right, cucumbers, pepperoni, ranch, cucumbers, pepperoni, Italian. Close the set. All right, let's make sure we have 8 outcomes here. 1, 2, 3, 4, 5, 6, 7, 8. All right, so I've got all 8 possible outcomes for my salad. All right, so now that you're familiar with some of the terminology that we're going to be using when talking about probability, I'm going to introduce you to something called classical probability. So classical probability is the most precise type of probability. This is as compared to something like experimental probability, where you are calculating probabilities based on data that was collected from an experiment in the real world, which obviously has its limitations. All right, so classical probability is the most precise type of probability. This is situations where all outcomes are equally likely to occur. And some classic examples of classical probability are things like flipping a coin, rolling a fair dice, and drawing a card from a deck. So you'll see those types of examples are the most precise type of probability. They're great examples to learn how to calculate probabilities with. Because we know that all of the outcomes in these experiments are equally likely to occur. Now, the the formula that I'm going to keep reminding you of for probability is that probability is simply calculated as success over total. So in each problem, you're going to have to ask yourself, what does a success look like here? What does the total look like here? All right, so we're going to remind ourselves in each problem that probability is success over total. Sometimes we might have to use that fundamental principle of counting to figure out what the total is. And then we also may have to think carefully about what a success looks like and think about how a success could occur in that scenario. All right, so starting off with a question that you're going to see in the homework, it says, what is the probability that a randomly selected person will have a birthday in March? Assume that this person was not born in a leap year. Now, sometimes I'll have people think of this in terms of months, and you could say like 1 out of 12, right? Because March is 1 out of 12 months. But if we were going to be even more precise, we could think of probability here as success over total, with the total being the total number of days in the year. All right, so we know that probability is success over total, and a success here means that the person was born in March. The total here means that when we're saying total, we're referring to 365 days in the year. All right, so 365 days in a year. Whoops, days in a year. As long as it's not a leap year. All right, and then a success here means the person was born in March. So we want to think about, okay, if we're doing this in terms of days, how many days are in March? All right, so if you don't have that little saying memorized, you might have to look in your calendar. But March has 31 days, and there are 365 days in a year, so it's 31 over 365. Now, this is always going to ask you for a simplified fraction. 31 over 365 does not simplify. One way that you can check that in your TI-84 is you'll just type in 31 divided by 365, and then you can hit the math button and choose the first option, which has a little arrow and it says frac. That means convert it to a simplified fraction. And in this case, it's just going to return back to you 31 over 365, and that just tells you that that fraction cannot be simplified. All right, so there's our first probability question. That's our answer here, 31 over 365. There we go. All right, let's look at a harder question. This question says a coin is tossed 6 times. So we know with a coin we can either get heads or tails. Right, so with a coin we have 2 possible outcomes for each coin. We could have heads or tails. It says, what is the probability of getting all tails? All right, so what is the probability of getting all tails? There's only one way that you could get all tails, right? It would be, if you kind of envision that tree diagram, it would be T, 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 T. All right, so 6 times you're tossing that coin, so 6 T's. All right, so we know that probability is success over total. So if I'm reading this first part of what I have written on the screen here, I would say probability of getting all tails is equal to success over total. All right, I know that there's only one way to have a success here, and that's to get all T's. But I need to figure out how many possible outcomes there are in my sample space. So if I toss a coin 6 times, how many possible outcomes are there? And so that's where the fundamental principle of counting is going to come in. All right, so again, each toss of the coin I'm thinking of as an individual box. So you can see I've got 6 boxes here, 1, 2, 3, 4, 5, 6. And each box represents a toss of the coin. All right, and so for each toss, I'm going to think about how many possible outcomes are possible, or how many outcomes are possible for that toss. All right, so for the first toss of the coin, I could get 2 outcomes, heads or tails. And then for the second toss, the same. Third toss, the same. So each time I toss the coin, I can either get heads or tails. All right, so now that I've got my boxes filled in, I can just multiply those numbers to get my total number of outcomes that are in my sample space. All right, so 2 times 2, let's see, 2 times 2 times 2 times 2 times 2 times 2 is 64. All right, so there's one way to get a success, and that's to get all T's, but there's 64 total outcomes in my sample space, so it's 1 out of 64 as my answer. All right, let's make it a little bit harder. It says, what is the probability of rolling a sum of 5 on a standard pair of 6-sided die? All right, so the word pair here indicates to us that we're working with 2 die, and we're assuming that these are fair 6-sided die. All right, so die is the singular for dice. All right, so we're talking about a 6-sided die here. All right, we know that probability is success over total. All right, so we're thinking, what is the success here? What is the total here? So a success is going to be that I roll a sum of 5. So we'll think about that in just a second. We'll go ahead first and get our total. All right, so finding the total number of outcomes in the sample space, I am rolling 2 die. So I've got 2 boxes, 1 for each die. On each die, it has 6 sides, so I have 6 possible outcomes for what I could get from rolling that die, right? Okay, so I can roll the die. I have 6 possible numbers that might show up, and then same for the second die. All right, I have 6 possible numbers that could show up. Now I just multiply those to find the total number of outcomes, which is 36. All right, so now I know what the denominator is going to be, but now I need to find the numerator. So I'm trying to think, how could I get a sum of 5 on 2 dice? All right, so I just wanted to take a second and like draw the little picture. If y'all remember how a dice looks, you could have 2 dots on the first die, 3 dots on the second die. Right, you could also flip that around and say maybe you had 3 dots on the first die, 2 dots on the second die. Right, you could also have 4 dots on one die and 1 dot on another, and then vice versa. All right, so you can see I have 4 on one die, 1 on another. Now, why am I not including 5 and 0 here? Why am I not including 5 and 0? That's because on a die, you're not going to have a blank side. The minimum number of dots for a side is 1. The maximum number of dots is 6. Right, so I'm not including 5 and 0 because on a die there is no side that has 0 dots. Okay, so there are 4 ways. There are 4 ways that I could get a success here. I could roll a 2 and a 3, or a 3 and a 2, or a 1 and a 4, or a 4 and a 1. All right, so there's 4 ways to get a success. So I have 4 out of 36 for my success over total, and 4 out of 36 is going to reduce to 1 over 9. All right, now backing off a little bit, giving you an easy one. A box contains 51 red marbles, 14 white marbles, and 81 blue marbles. If a marble is randomly selected from the box, what's the probability that it's red? All right, so express your answer as a simplified fraction. All right, so we're looking for the probability of getting a red marble. We know that that's success over total. Success over total. Well, let's figure out the total number of dice. Not dice, y'all, I'm so tired. The total number of marbles in the box. All right, so we're going to add these together. 51 plus 14 plus 81. That's all the marbles in the box. If you add that together, you get 146. All right, and so success over total. How many red marbles are in the box? 51. Total is 146, so it's 51 over 146 for success over total. All right, and then just wanted to give you an example with a table. So here it says a telemarketer's computer selects phone numbers at random. The telemarketer has recorded the number of respondents in each age bracket for one evening in the following table. All right, so this person is at work, they're calling people, and every time someone picked up the phone, they recorded what age bracket they were in. All right, so that's what table we're looking at here. It says, what is the probability that the next respondent will be between 18 and 35? This is an example of what we would call experimental probability. And that just means that the probability that we're calculating is based on some previously completed experiment. So the accuracy of this probability is completely dependent on the accuracy of the experiment, right? So if another telemarketing company, maybe that calls during the day, because this one was during the evening, another telemarketing company may have slightly different probabilities because they may have different people answering the phone in the morning versus in the evening, right? So experimental probability, less accurate, but still a type of probability that folks will use in real statistical studies. All right, so we are finding the probability that our next respondent or next person that answers the phone is between 18 and 35 years old. So I know that that's success over total, right? So I'm thinking success over total. Total is going to be the total number of people that are represented in this table. So you're just going to add those values up, 20 plus 29 plus 36 plus 56 plus 53. And that adds to 194. And a success here is that the person was between 18 and 35, right? So let's see how many people in our table are between 18 and 35. That's these 29 people in the age bracket 18 to 25, and then the 36 folks that are in the age bracket 26 to 35. Right, so we're going to add those two numbers together to get our total number of successes. Right, so success is going to be 29 plus 36 over 194 for our total, and then 29 plus 36 adds to 65. So 65 over 194, that doesn't reduce, so you can leave it as 65 over 194. All right, so that has been a very brief introduction. Well, I say brief, it was 30 minutes, but just a short introduction to probability. We will get into more specific types of probability, more specific types of problems, and the more complicated ways that we can compute the probability of different events occurring, or something that we call conditional probability, which is where what's the probability that something occurs given that you have some prior information about the event. So we'll get into those more complicated topics in the next few sections. But for now, if you have any questions, I hope you will email me and let me know. And I'll see you guys in the next video.